In this video, we are going to discuss earthquakes. Some earthquakes can cause massive amounts of damage to building and infrastructure. The energy translated from earthquakes can cause liquefaction of the soils and cause buildings to topple. It is important to understand the science behind earthquakes to lessen the danger to life and property. When rocks adjacent to the boundary quietly flex, like a stick bent between your hands, to accommodate the motion until suddenly, like a stick that snaps after you bend it too far, the rock breaks, and a large amount of slip on a fracture takes place in a matter of seconds to minutes. So the earth's shaking is caused by rapid release of energy that moves outward as expanding spheres of waves, and this waveform energy can be measured around the globe. Earthquakes are very common on the planet. They occur every day. More than 1 million detectable earthquakes occur each year. The majority of earthquakes are results of tectonic plate motion. Geologists refer to a fracture on which sliding takes place as a fault. The fault involved on March 11th event delineates the boundary between Honshu and the Pacific Plate. The sudden breaking and sliding of rock along a fault produces energy that propagates through the crust in the form of vibrations. In essence, these vibrations resemble the shock waves that travel through the breaking stick into your hands. In the earth, vibrations can race through the crust at an average speed of 11,000 kilometers per hour, 10 times the speed of sound in the air. When the vibration produced on the March 11th event reached Japan, the land surface lurched back and forth and bounced up and down for over a minute. Bottles and plates flew off shelves and crashed to the floor. Buildings twisted and swayed. Ceilings and facades fell in a shower of debris. Dust rose from the ground, creating a fog-like mist. Power lines stretched and sparked, and weaker buildings collapsed. In addition, several natural gas tanks and pipes broke, sending flammable vapors into the air, and in some places the gas ignited in billows of flame that set fire to damaged buildings. Earthquakes are a fact of life on the planet Earth. Almost 1 million detectable earthquakes happen each year. Most are a consequence of plate movement. They punctuate each step in the growth of mountains, the drift of continents, and the opening and closing of ocean basins. Fortunately, most cause no damage or casualties, either because they are too small or because they occur in unpopulated areas. But a few earthquakes per year rattle the ground sufficiently to crack or topple buildings and injure the occupants. Every 5 to 20 years, on average, a great earthquake triggers a horrific calamity. In fact, during the past 2 millennia, ground shaking, tsunamis, landslides, fires, and other phenomena caused by earthquakes have killed over 3.5 million people. The sudden displacement of the seafloor off Japan's coast displaced a massive amount of ocean water and produced immense water waves known as tsunamis. When these waves washed over the land, they became a roaring jumble of water and debris that submerged low-lying areas as far as 10 kilometers from the shoreline. In the end, the immensity of the devastation from the Tohoku earthquake was almost beyond comprehension. What causes earthquakes? Seismicity, or earthquake activity, occurs due to 1. A sudden motion along the newly formed crustal fault. 2. Sudden slips along an existing fault. 3. A mineral phase change in rock, such as the change that occurs when calcite converts to dolomite. There's about a 13% reduction in volume. 4. Movement of magma in a volcano. 5. Volcanic eruption. 6. Giant landslides. 7. Meteorite impacts. And 8. Nuclear detonations. Fault slip is the most common cause of earthquakes. When describing the location of an earthquake, seismologists use 2 terms. First, we define the point on a fault which rock starts to rupture and slip as the hypocenter, or focus of an earthquake. See the figure on the left. Simplistically, we can picture the focus as the place inside the earth from which the earthquake energy, in the form of vibrations, begin to propagate. Secondly, we define the point on the surface of the earth that lies directly above the focus as the earthquake's epicenter. We can portray the position of an epicenter as a spot on the map. See the figure on the right. Faults are like planar breaks in blocks of crust when two blocks slip past one another. Most faults have a slope, although some faults have vertical slopes. On a sloping fault, crustal blocks are classified as footwall, block below the fault, and hanging wall, block above the fault. The fault type is based on relative block motion. For normal faults, the hanging wall moves down relative to the footwall. Normal faults result from extension, pulling apart or stretching of the Earth's crust. The fault scarp is the exposed portion of the slip face. The fault line or fault trace is the line marking the intersection of the hanging wall block with the footwall block. The displacement is the amount of slippage. The fault type is based on relative block motion. For normal faults, the hanging wall moves down relative to the footwall. Normal faults result from extension, the pulling apart or stretching of the Earth's crust. The fault scarp is the exposed portion of the slip face. The fault line or fault trace is the line marking the intersection of the hanging wall block with the footwall block. The displacement is the amount of slippage. Reverse faults occur when the hanging wall moves up relative to the footwall. Reverse faults occur from compression, squeezing or shortening of the Earth's crust. If the slope or dip of the fault is steep, greater than 35 degrees, the fault is considered a reverse fault. A thrust fault is a special kind of reverse fault with a slope or dip less than 30 degrees. Reverse faults are common in compressional tectonic or mountain settings. Strike slip faults are the result of tensional stress when one block slides laterally past another block in the strike direction. The fault surface is nearly vertical. Slip is measured along the surface. Displacement is the amount of movement across a fault. Displacement is often called offset and may occur in one large movement, or the displacement may be cumulative over time. A black and white photograph and an illustration show examples of fault displacement. The photograph shows a large gap in a broken lawn fence in a hilly area. The illustration shows the same setting as the photograph. In both images, the planes of the fence's two pieces are parallel, and the plane of the gap between the two fence pieces is perpendicular to the planes of the fence pieces. In the illustration, a black line along the ground labeled fault trace is perpendicular to the fence pieces plane and connects the bases of the fence posts on the gap's edges. The portion of the fault trace line that is between the fence pieces is labeled displacement. In the image, the fence was displaced along the trace of the fault at least 6 feet or more. Faults are found in many places in the crust. Faults are either active when ongoing stresses produce motion, or inactive faults where motion has occurred in the geologic past. A fault trace shows the fault intersecting the ground. Displacement at the land surface creates a fault scarp. Not all faults reach the surface. Blind faults are invisible. An aerial photograph shows the area around a dirt road. several cracks across the middle of the road. These ruptures form where the fault broke the ground surface. Elastic rebound along the Hayward Fault in California. A right lateral strike slip fault. Elastic rebound is a bend, break, snapback perspective. As the blocks are moving, they bend the opposing block due to friction. When rock strength is exceeded, then breakage occurs and the land on either side of the trace snap back to the original alignment perpendicular to the trace. However, it is not possible to know how much bend a given interval can take. This map shows the locations of small tremors or foreshocks. The inset shows magnitude of the earthquake in relation to the diameter of the circles. The larger the diameter, the greater the magnitude of the quake. A major earthquake may be preceded by foreshocks, smaller tremors indicating crack development in rock and may forewarn of an impending large earthquake. Aftershocks usually follow a large earthquake and they may occur for weeks or years afterwards. How much does a fault slip during an earthquake? Well, it depends on the size of the earthquake. Larger earthquakes have larger areas of slip, with displacement greatest near the hypocenter. Displacement diminishes with distance. Fault slip is cumulative. Some faults can offset rocks by hundreds of kilometers given over geologic time. For example, the Pacific block of the San Andreas Fault will be Newport's neighbor, that's Newport, Oregon's neighbor, in 19 million years. In the upper lithosphere from 15 kilometers to the surface, the rock is brittle. The rock fractures or breaks under stress. However, at depths in the lithosphere below 15 kilometers, the rock is more ductile or behaves more plastically. It stretches or deforms without breaking. This is called ductile deformation. The rocks are hot enough to stretch and bend plastically, like taffy. In the image, the rock has been severely compressed and folded. There are two types of body waves that pass through the interior of the Earth, P waves and S waves. P waves are primary or compressional waves. The waves move or propagate through the Earth by compressing or expanding the rock as it moves away from the earthquake hypocenter. Much like a slinky moves across the floor by compressing or expanding the coils parallel to the wave or slinky's direction of motion. P waves are the fastest waves and they can travel through solid rock, liquid, or gases in voids. S waves are the second type of body wave. They move much like a wave moves along a rope when one side is tied to a wall and the other end is moved vertically up and down. The single waves move up and down along the entire rope from your hand to the wall. So, the amplitude of the wave is perpendicular to wave travel direction. S waves are slower than P waves, and they travel only through solids. S waves cannot move through liquids or gases. Surface waves travel along the Earth's surface. There are two types of surface waves, L waves or love waves, and R waves or Rayleigh waves. L waves or S waves are shear body waves that intersect the land surface. They create a side-to-side motion like a snake moving. The side-to-side movement or motion is perpendicular to the direction of movement. They are larger amplitude waves with amplitudes measured up at 2 meters. They can easily snap gas, water, and sewage lines. Rayleigh waves are the second type of surface wave. They follow love waves in propagation. In other words, they are slower in velocity than love waves. They are P waves that intersect the surface and cause the ground to ripple up and down like ocean swells coming towards the shore. They move up and down with a retrograde or counterclockwise motion linearly and parallel to wave direction. Both Love and Rayleigh waves die out with depth. We use seismometers to measure movement of the Earth's surface. A modern seismometer measures both up and down motion and side-to-side motion with a fixed electric coil inside of a spring-loaded magnet that produces an electric signal that can be recorded digitally. The devices are very sensitive and can detect motion that humans cannot sense. The deflections traced by the seismometer provide a record of an earthquake called a seismogram. It is a continuous graph with the y-axis, the vertical axis, recording amplitude of the wave, and the x-axis, the horizontal axis, recording arrival time of the wave. An arrow labeled time points from left to right. The paper has a continuous red path traced from left to right. From left to right, the path traced on the paper begins horizontally, then at a point labeled P wave arrival begins jutting repeatedly but inconsistently up and down slightly. At a point labeled S wave arrival, the path juts up and down higher and lower than before. At a point labeled surface wave arrival, the path juts up and down even higher and lower than before, and waves begin increasing in amplitude. These are labeled surface waves. Eventually, the amplitude begins decreasing, approaching the amplitude of P waves. Finally, an aftershock consists of several quick, sharp juts up and down to amplitudes reaching slightly higher than S wave and is followed by a return to P wave amplitudes. Different types of seismic waves travel at different velocities. The first wave to be recorded are the P or primary body wave, followed by the S or secondary or shear body wave, followed by the surface waves. As mentioned, the Love waves arrive before the Rayleigh waves, so P wave velocity is the fastest and Rayleigh surface waves are the slowest. The greater the distance between the epicenter and the seismometer station, the longer it takes for the earthquake waves to arrive, and the greater the delay between P wave and S wave arrival times. A graph with distance between epicenter and seismometer in kilometers on its horizontal axis and travel time in minutes on its vertical axis show two curves labeled P, faster, and S, slower, and a point on each curve corresponding to 3 stations. Both curves rise from left to right at a decreasing rate, beginning at 0, 0. At any positive horizontal coordinates, the curve labeled S, slower, is above and more steep than the curve labeled P, faster. The data from the graph is as follows. Station 1, distance 2,000 kilometers, S time 4 minutes 6 seconds, P time 7 minutes 25 seconds. Station 2, distance 4,000 kilometers, S time 6 minutes 58 seconds, P time 12 minutes 36 seconds. Station 3, distance 6,000 kilometers, S time 9 minutes 21 seconds, and P time 16 minutes 56 seconds. The portion of the dashed line between the curves for each section is solid and labeled S minus P time. The S minus P time increases as distance from the epicenter increases. Three scales are used to measure the magnitude or size of an earthquake. The Mercalli intensity scale, based on historical hearsay evidence. The Richter scale gives rapid local intensity of an earthquake, and the moment magnitude scale provides the most accurate representation of the earthquake size. The Mercalli intensity scale was developed in 1902 by Giuseppe Mercalli as a scale to measure intensity by assessing human perception of shaking and the damage that an earthquake caused. He assigned Roman numerals to different levels of damage. He found that damage occurred in zones of severity and that damage diminished with distance from the epicenter or zone of highest damage. The Mercalli intensity scale is very subjective, but is used to describe historical earthquakes that occurred before seismometers and seismographs were in existence. A more accurate representation of an earthquake's magnitude is the Richter scale. Charles Richter developed the Richter scale in 1935. His scale worked like a seismogram, measuring the maximum amplitude of seismograph motion by a particular type of seismometer normalized at a distance of 100 kilometers or 62 miles from an earthquake. The Richter scale methodology allowed scientists to make quick assessments of an earthquake's magnitude. It is based on a logarithmic scale with each magnitude times greater than the previous scale. It is based on the time between the arrival of the first P wave and the first S wave in seconds, correlated to the amplitude in millimeters of the largest surface or Rayleigh wave. A line going from the S minus P scale to the amplitude scale crosses over the magnitude scale normalized to thousands of earthquakes. The placement of the three scales have been standardized to give uniform readings. This method works well for earthquakes whose focus lies close to the Earth's surface and whose epicenter lies fairly close to the seismometer station. The method cannot accurately define the size of extremely large earthquakes because for these earthquakes, the scale gives roughly the same magnitude regardless of how large the vibrations actually are. Because of the problem, seismologists developed the moment magnitude scale. The Richter scale methodology allowed scientists to make quick assessments of an earthquake's magnitude. It is based on a logarithmic scale with each magnitude times greater than the previous scale. It is based on the time between the arrival of the first P wave and the first S wave in seconds correlated to the amplitude in millimeters of the largest surface or Rayleigh wave. A line going from the S minus P scale to the amplitude scale crosses over the magnitude scale normalized to thousands of earthquakes. The placement of the three scales have been standardized to give uniform readings. The method works well for earthquakes whose focus lies close to the Earth's surface and whose epicenter lies fairly close to the seismometer station. The method cannot accurately define the size of extremely large earthquakes because for those earthquakes, the scale gives approximately the same magnitude regardless of how large the vibrations actually are. Because of this problem, seismologists have developed the moment magnitude scale. The moment magnitude scale is based on the physical parameters of the earthquake event. Geologists go to the field and measure the following parameters to obtain the seismic moment. The rock strength measured in newtons per square meters obtained from rock cores along the trace of the fault. The area of the fault along which movement occurred during the earthquake measured in square meters. These measurements are obtained from cores and elevations along the trace of the fault. Finally, the average displacement of the fault, the same as the average slip of the fault in meters. These variables together give the seismic moment in Newton per meters. While magnitude measures of either Richter and moment magnitude represent changes of 10 times, in actual energy, the difference between the Richter to moment magnitude number is 32 times. So an M7 has 100 times more seismic moment or magnitude than an M5, 10 times 10, in both scales. However, the measurements made for the moment magnitude compute the energy difference to be 1024, or 32 times 32. This chart illustrates the magnitude of certain events translated into their moment magnitude or logarithmic scale on the x-axis and the energy released in kilograms of TNT on the y-axis. In parentheses is shown as tons of TNT. For example, a lightning bolt can register a magnitude of 3 with energy released of about 1.6 tons of TNT. The Loma Prieta earthquake had a moment magnitude of 7 and the energy released of about 410,000 tons of TNT. The largest earthquake on record off of Chile in 1960 had a moment magnitude of 9.5 and an energy equivalency of 6.5 billion tons of TNT released. The largest H-bomb released was equivalent to 8.0 magnitude earthquake and with 52 million tons of TNT. Small earthquakes are far more frequent than large earthquakes. There are roughly 100,000 M3 earthquakes per year, and there are only 32 M7 earthquakes per year. On the left is a world map that shows shallow, intermediate, and deep earthquakes with dots of different colors. Most earthquakes appear in patches or lines along plate boundaries. Patches of shallow earthquakes occur in the Atlantic Ocean halfway between the continents, along the west coast of North America, in Philippines and Indonesia, and throughout the Mediterranean region of Europe. Patches of intermediate earthquakes occur on the west coast of Central and South America, in the Caribbean, in the islands of East and Southeast Asia, and in New Zealand and the Pacific Islands to the north. Patches of deep earthquakes occur off the east coast of Asia around Japan and the far east of Russia, in Indonesia, and in the Pacific Islands north of New Zealand. An area near the Black Sea is labeled Alpine Himalayan collision. Earthquakes occur at plate boundaries, at divergent boundaries. Figure on the right, two kinds of faulting occur. Normal faults parallel to ridge axis and along strike slip faults along transform boundaries. These are shallow faults less than 10 kilometers deep. At shallow depth of convergent plate boundaries, there are both normal faults that form as the downwarping plate bends, and large thrust faults occur as the non-subductible overriding plate overrides or thrusts over the downward plate. Also, as the downwarping plate descends, it pulls or warps the edge of the overriding plate downwards with it. Over time, the overriding plate will snap back, creating large magnitude earthquakes and tsunamis, which we will talk about later in the lecture. At the Cascadia Fault, the convergent zone west of Oregon, the last major movement of the plate was in 1700, with an estimated Mercalli magnitude of 9.0. For comparison, there were 0 magnitude 8 to 8.9 earthquakes in 2020, 9 magnitude 7 to 7.9 earthquakes in 2020, and 100 magnitude 6 to 6.9 earthquakes in 2020 around the world. At convergent plate boundaries, intermediate and deep earthquakes are also common. At the Wadati-Benioff zone, earthquakes trace the descending slab. At intermediate depths, from 20 to 300 kilometers, the downgoing slab is still cold and brittle. At depths greater than 300 kilometers and to a depth of 660 kilometers, earthquakes are rare but still occur. The earthquakes occur as mineral phase changes that occur in ultramafic rock, peridotite. The olivine chemically phase change into a denser mineral called wadsleyite and ringwoodite due to heat and intense pressure causing shrinkage and earthquakes. Remember that at transform plate boundaries, plates slide past each other. The earthquakes occur at shallow crustal depths. Most transform strike-slip faults occur at mid-ocean ridges. However, some cut through thicker continental crust. Some large continental transform faults are the San Andreas Fault in California, the Alpine Fault in New Zealand, and the Anatolian Fault in Turkey. Large disasters are commonly associated with continental transform boundary faults. For example, the San Andreas Fault cuts through western California with the Pacific Plate shearing north and the North American Plate moving south. Is it a right lateral or a left lateral strike-slip fault? If you said right lateral or you thought right lateral, you would be correct. It is a very dangerous fault that has hundreds of earthquakes each year. The 7.0 magnitude Loma Prieta earthquake occurred in 1989, causing $11 to $12 billion in damages. The 1906 San Francisco earthquake that destroyed San Francisco was a 7.9 earthquake. Continental stretching creates normal faults in rift valleys. The rifting is similar to rifting at mid-ocean ridges. Mantle upwelling, like at mid-ocean ridges under continents, causes the land mass to bow and arc from heating, and like a balloon, stretching thinner and thinner. The image on the left. Eventually, failure occurs, leading to a series of parallel faults on either side of the rift zone. Over time, the rifting will continue to widen and reach the ocean, filling the rift valley with seawater. Very similar to the opening of the Red Sea, the image on the right. Given more time, it will open even further, creating an ocean basin like the North Atlantic was created after the breakup of Pangaea. The earthquakes in continental rift zone impact people. The Basin and Range Province, found in southeastern Oregon, Nevada, Utah, and Arizona, is an example of a continental rift zone in late early stage, reaching down to the Sea of Cortez. Thrust faults develop when two continents collide when they meet at convergent zones. The continental lithosphere compresses along thrust faults, creating huge mountain chains like the Himalayas and the Alps. They also create large earthquakes and landslide hazards. About 5% of earthquakes are located on continents and not near plate boundaries. We are not sure why these earthquakes develop. They may be due to remnantal crustal weakness in failed rift zones like the lower Mississippi Valley, stress transmitted to lithosphere from the asthenosphere, or due to isostatic adjustments such as the removal of continental glaciers at the end of Pleistocene. Some of these earthquakes can be quite large, like the 3 magnitude 7 earthquakes that struck New Madrid, Missouri in 1811 and 1812. The zone is still active, averaging more than 200 measured seismic events per year. The largest since then within the New Madrid fault zone was a magnitude 5.4 earthquake in southern Illinois in 1968. People have influenced seismic events. Earthquakes have been initiated by changing groundwater pressure regimes, such as overpumping aquifers, or by adding the pressure of a dammed reservoir, which can cause water to lubricate pre-existing faults, or by fracking to produce petroleum. Earthquakes kill people and destroy cities. The damage can be widespread, horrific, and heartbreaking. This is Anchorage, Alaska, after the 1964 magnitude 9.2 earthquake. Notice the block on the left dropped down in relation to the block on the right. What kind of fault would this be? If you thought normal fault, you would be correct. How does earthquake damage occur? These cartoons illustrate that the shaking that occurs due to the different seismic waves reaching the surface of the planet. In illustration A, the flat horizontal layers beneath the surface bend upward. An arrow beneath the surface indicates that wave propagation is upwards, and a double arrow on the surface indicates that the vibration direction is up and down. Vertical P waves cause the ground to go up and down. A bridge on the surface lifts up as a result. In illustration B, we see flat horizontal layers beneath the surface. An arrow beneath the surface indicates that the wave propagation is upward, and a double arrow on the surface indicates that the vibration direction is left and right. Vertical S waves cause the ground to go back and forth. A tower on the surface bends left and right as a result. In illustration C, flat horizontal layers beneath the surface that extend outward in a repeated wavy pattern. Closer to the surface, the waves extend out further. The surface is flat. An arrow beneath the surface indicates that wave propagation is left and right, and a double arrow beneath the surface indicates that the vibration direction is up and down, or is outward rather. Love waves undulate the ground laterally. On the surface, a straight road breaks into pieces that follow a wavy, repeating curve pattern. In illustration D, the wavy layers with waves that become less pronounced as depth increases. An arrow beneath the surface indicates that wave propagation proceeds from left to right. Arrows just beneath the surface point in small counterclockwise circles. Rayleigh waves make the ground surface roll in wave-like motions. The surface has rolling hills with peaks centered at the rolling arrows. On the surface, a tower on the peak of the curve bends left and right and electric lines snap. Severity of shaking and damage depends on the magnitude or energy of the earthquake, the distance from the hypocenter, the intensity and duration of the vibrations, and the nature of the subsurface material. Solid bedrock transmits seismic waves quickly and equate to less damage. Unconsolidated sediments reflect and refract waves, which amplifies damage. S waves and surface love waves with side-to-side direction of movement can cause buildings to pancake and bridges and overpasses to topple. Upper left, the before illustration shows two stacked sets of vertical girders supporting a horizontal girder swaying from left to right. The after illustration shows the girders collapsed into a pile. The photograph from Turkey shows a multi-story building that has collapsed into a pile with floors stacked atop one another. Lower left, the before illustration shows a car on a concrete bridge elevated by a single central support. Arrows indicate that the support sways from side to side, and the top edges of the bridge swing rotationally. The after illustration shows the support fallen to the right, and the top part of the bridge and the car on their sides. The photograph from Japan shows an elevated highway, a portion of which has fallen onto its right side, with support beams on the left side uprooted from the ground. P waves and Rayleigh waves are with up and down direction cause bridges to collapse and masonry walls to break apart. Upper right, the before illustration shows a concrete bridge supported by two vertical support beams with a double arrow pointing up and down. The after illustration shows the bridge held at a slight angle by the beams, which are shorter, and whose middles have been crushed and are surrounded by the rubble at the bottom. The photograph from California shows a concrete bridge support that has crumpled and been crushed at the top and is surrounded by rubble at the bottom. Lower right, the before illustration shows a brick building with central interior bricks falling and bricks throughout separated as a double arrow indicates ground motion from left to right. The after illustration shows the building collapsed into a pile of bricks. The photograph from Armenia shows several rows of houses, all collapsed unto themselves as people walk a broad street between them. Earthquakes can cause landslides and avalanches. Landslides frequently accompany earthquakes in steep uplands. The shaking causes the material on steep slopes to fail. A photograph shows a part of a house on flat land at the edge of a steep slope of mud and dirt. Part of the house is broken off along the slope, and the pieces of the house roof, walls, and windows lie in ruins on the slope. Liquefaction takes place when loosely packed, waterlogged sediments at or near the ground surface lose their strength in response to strong ground shaking. Liquefaction occurring beneath buildings and other structures can cause them to fall during earthquakes. The photograph on the left shows several 5 to 6 story buildings, some of which have tilted backwards and one of which has fallen backwards onto its side, exposing its base. All are surrounded by mud. An aerial photograph on the right shows a dark area of collapsed buildings and mud along a coast, with snow and trees behind. Earthquake shaking topples stoves, candles, power lines, along with broken gas mains and fuel tanks, can start major fires. Often firefighters are powerless to combat the fires because the infrastructure of water, sewer, electricity, and roads are destroyed. This photograph shows a large fire and dark smoke pouring from a structure on the shore of a large coastal city. Tsunamis are giant waves caused by earthquakes or volcanic eruptions under the sea. Out in the depths of the ocean, tsunami waves do not dramatically increase in height, but as the waves travel inland, they build up to higher and higher heights as the depth of the ocean decreases. The speed of tsunami waves depend on ocean depth rather than the distance from the source of the wave. Tsunami waves may travel as fast as jet planes over deep water, only slowing down when reaching shallow waters. While tsunamis are often referred to as tidal waves, this name is discouraged by oceanographers because tides have little to do with these giant waves. The catastrophic Indian Ocean tsunami, December 26, 2004, was the largest earthquake of a subduction trench off the northwest Sumatra coast in 40 years, with a magnitude of 9.0. The displacement was 15 meters, about 49 feet, and the trace exceeded 1,300 kilometers in length. Because of the lack of warning tsunami, or rather the lack of tsunami warning system in the Indian Ocean, close to 250,000 lives were lost. The photograph on the left shows two wave crests approaching a beach as people attempt to run away from them. The illustration on the right shows the nearly vertical crest of a large wave. The crest is greater than the height of 7 people. After the Sumatra tsunami, scientific modeling and more detecting devices around the world have helped to predict when, the size, and where tsunamis will strike coastlines around the world. Tsunami detectors are placed on the seafloor that measure pressure increases due to change in sea thickness at the sensor. Buoys on the sea surface relay this information to tsunami warning centers. These predictions will certainly help avoid the huge loss of life that occurred due to the Sumatra tsunami. Can we predict earthquakes? We can predict earthquakes in the long term from tens to hundreds of years. However, unfortunately, we cannot predict in the short term, in the realm of hours or even weeks. Hazards can be mapped to assess risks that are beneficial for developing building codes, for land use planning, and for disaster planning. A world hazard map that illustrates the areas of the world with the highest hazards. They are the western halves of North and South America, the Mediterranean region, Iran, the mountainous region from Central Asia to eastern India, Japan, Philippines, and New Zealand. The areas of the world with the lowest hazards are Greenland, Central North America, Western South America, Eastern Europe, Russia, and most of Africa and the Arabian Peninsula. The areas in the United States with the highest hazard, image on the right, are in the west, especially Hawaii, Alaska, California, which is the site of the San Andreas Fault, the California-Nevada border, Washington, Utah, the Idaho-Wyoming border, and the area around Madrid, Missouri. The areas with the lowest hazard are throughout the Midwest, the Deep South, and the Northeast. Currently, there are no reliable short-range predictors or forecasting ability. However, earthquakes do have precursors, such as clustered foreshocks, crustal strain, stress-triggering events, level changes in wells, the accumulation of radon and helium gases in wells, and strange or unusual animal behavior. The map on the right shows faults and shaking intensity in Haiti. The area around the epicenter experienced shaking intensity of 9. The areas away from the epicenter experienced shaking intensities ranging from 4 to 8, declining with distance from the epicenter. We can't stop them, but we can be ready for them by understanding what happens during an earthquake. By mapping active faults in areas likely to liquefy from shaking, developing construction codes to reduce building failures, and regulate land use to control development. In the figure are 4 illustrations that show aspects of various structures that strengthen them against vibration and collapsing. The first illustration shows the wooden frame of a corner of a house as several connected wooden planks, mostly oriented horizontally and vertically. The frame includes an across-the-top metal brace that overlaps corners, strapping around corner studs, and a corner double brace on the base. Adding corner struts, braces, and connectors can substantially strengthen a wood frame house. The second illustration shows a 6-story building. On one side, the building has 2 vertical beams along the edges and horizontal beams at the bottom, at the top, and between the 3rd and 4th floors. Between each pair of horizontal beams, 2 diagonal beams labeled cross beams connect opposite corners. Buildings are less likely to collapse if they are wider at the base and if cross beams are added for strength. The third illustration shows a vertical column sticking up from a cement base with a horizontal surface on top that extends rightward. Cable is wrapped around the column, and an anchor bolt on top of the surface secures a rod that passes through the surface and into the column. Wrapping a bridge support columns and cable and bolting the span to the columns will prevent the bridge from collapsing so easily. The last illustration shows a 6-story building atop a horizontal cement layer. There are 4 adjacent rollers underneath the cement layer. Horizontal springs are immediately to the left and right of the rollers. Placing buildings on rollers or shock absorbers lessens the severity of the vibrations. Finally, remember that we can't stop earthquakes, but we can be ready for them. How can we do this? By training the community in earthquake preparedness, by running preparedness drills, by educating individuals on safe behavior and responses, and by keeping viable stores of emergency supplies.